Welcome to GenAI Level Up, the podcast where we decode the future of artificial intelligence one breakthrough at a time.
Whether you're just starting your AI journey or you're a seasoned expert, you've come to the right place. Our mission is to make the complex world of generative AI accessible to everyone, everywhere.
In each episode, we dive deep into the foundational concepts, the latest research, and the transformative applications that are shaping our world. It's time to get smarter, faster. Let's level up together.
Welcome to the Deep Dive, where we crack open the densest research papers and pull out the knowledge you need. Today, we're getting into what might be the single most frustrating challenge for large language models right now.
Which is the fact that they're basically static. They're frozen in time the moment they're deployed.
Exactly. They have all this incredible knowledge, but they really struggle to learn anything new or pick up new skills once they're out in the wild. Their long-term knowledge base is, for all intents and purposes, locked.
And if you, the listener, have ever tried to teach an LLM something genuinely new, something that wasn't in its training, you've run straight into this wall.
Well, the sources we're looking at today propose a, frankly, radical solution to smash right through it. It's a paradigm they call nested learning, or NL for short.
NL completely reframes how we think about these models. It's a shift away from just, stacking more and more layers.
Yeah, what exactly?
To seeing them as integrated systems of, nested, multi-level optimization problems.
Mm-hmm. And that's our mission for this deep dive, to unpack what that actually means. We're going to show you how this approach, which is really heavily inspired by neurophysiology, could lead to models that can actually self-improve.
Right. And it leads to some really novel architectures, like one they call HOPE, and even changes how we should think about something as basic as an optimizer.
So this is about more than just what LLMs know. It's about how they're built to learn, or, maybe more importantly, how they're built to stop learning. Okay, so let's frame the problem first. The illusion of static learning. We've all seen the progress, bigger models, transformer architectures, these scaling laws that seem to work.
But the authors make a really sharp point. Just piling on more layers isn't the silver bullet we thought it was.
You get a higher parameter count, sure.
But that doesn't mean you're changing the underlying, the computational depth. It doesn't guarantee the model can suddenly adapt faster or learn continuously. It hasn't solved that problem at all.
And here's where the source material gets so compelling. They use this incredible analogy to explain the failure. They say current LLMs suffer from something that looks a lot like Anterograde amnesia.
Anterograde amnesia in people is when you can't form new long-term memories. You remember your childhood, everything up to a certain point, but new experiences they don't stick.
So how does that map to a language model? It's surprisingly direct. An LLM's knowledge is crapped in two places.
First, you got the immediate context, whatever fits in that window. That's its very, very short-term memory. It's transient.
And second, you have the mountain of knowledge baked into its MLP layers from pre-training. That's the long-past unchangeable memory.
And there's no bridge. Nothing that happens in that short-term context window can ever make its way into the long-term knowledge base.
This deficit is what pushed the researchers to look at, the human brain, which is obviously the gold standard for learning.
Right. Our neuroplasticity comes from two very different memory consolidation processes that work on different clocks, different timescales.
You have the fast one, the online consolidation.
That's synaptic. It happens right away to stabilize a new, fragile memory as it comes in.
But then, and this is the crucial part, there's the offline consolidation.
Or systems consolidation. This is the slower process, maybe when we sleep, where memory gets reorganized, strengthened, and woven into everything we already know.
And that's the fatal flaw in a standard transformer. All the new information you give it in the context, it just never gets a chance to impact those long-term parameters in the feed-forward layers.
It's like the online consolidation mechanism is broken. It can't write to long-term storage. The model is constantly seeing new things, but it can't acquire new knowledge. It's stuck.
So nested learning is the framework they designed to build that bridge, to give the model that missing capacity for self-modification. Okay, let's unpack nested learning itself. It sounds pretty abstract, but the core idea is viewing the model as this hierarchy of optimization problems.
And central to that whole view is the concept of associative memory.
Which they define very simply.
Right. It's just an operator, let's call it M, that maps a set of input keys, K, to a set of output values, V. Just think of a lookup table that's always being updated.
So that's the structure. But what about learning itself? The sources draw a really sharp line here from neuropsychology.
They do. They define memory as just a neural update from an input. But learning is the process of acquiring effective and useful memory.
That's a great distinction. So learning is basically a form of what? Data compression.
Essentially, yes. High-dimensional data compression. The optimization is trying to find the most efficient way to represent all those key-to-value mappings in a much smaller parameter space.
What's so fascinating is how universal this idea turns out to be. NL argues that even the simple gradient-based optimizers we use every day are actually associative memory modules.
Exactly. They are memory modules that are designed to compress gradients. Take standard gradient descent, training a one-layer MLP with it. That's a one-level associative memory.
Simple enough. But what happens when we use something a little more complex, like gradient descent with momentum?
Now it gets interesting. Momentum immediately creates a two-level optimization process. This is the heart of nested learning.
2 levels. How?
The slow weight update, the main W parameter, that's your outer level update. It's operating on the main weight matrix.
And the momentum term itself. The little.
That's the inner level associative memory. Its entire job is to compress the history of past gradients. It's a tiny, keyless memory that operates on a much faster time scale than the main weights.
I have to ask, though, because replacing a simple linear operation with a whole new trainable module, that sounds like it could be really computationally expensive. Is the trade-off worth it?
That's a great point. And yeah, the researchers definitely thought about that. The benefit isn't about size, it's about expressiveness.
How so?
Well, NL points to things like deep momentum gradient descent, or DMGD. You take that simple memory in the momentum term and you replace it with a small MLP.
An MLP just for remembering how gradients behave.
Yes. And that small network can capture really complex nonlinear patterns in the gradients without blowing up the parameter count or slowing things down too much. It's not about more memory. It's about smarter memory.
And the sources even show that just adding a nonlinearity to the output of that momentum term is mathematically the same as some advanced optimizers like muon.
Exactly. We've gone from thinking of optimizers as fixed math rules to seeing them as trainable, nested memory components.
But nested learning isn't just about the optimizer, right? It's about redesigning the whole architecture to handle these different timescales.
It is. A great example is linear attention.
Okay, we all know attention is key. How does NL change how we look at it?
Well, if you train linear attention with regular gradient descent, NL shows you it naturally splits into a two-level optimization.
What are the 2 levels there?
The outer loop is optimizing the slow parameters, the big projection layers, YKWV, WQ.
The parts that hold the abstract long-term knowledge.
Precisely. And the inner loop is optimizing the attention matrix itself, which is the fast associative memory M sub T. It's just compressing the current context, so it needs to be quick.
And this brings us to what I think is the most important concept here. The update frequency, which they call F sub A. This is how NL actually organizes the system.
Yes, F sub A is the metric. It's used to sort every component into a level. Higher levels mean lower frequencies.
So slower updates.
Much slower updates. And this difference in timescale gives each level its own context and, critically, an exclusive gradient flow.
Okay, exclusive gradient flow. Why is that so important? It almost sounds like you're intentionally walling off parts of the model from each other.
You are, and you have to. This is the whole defense against that amnesia problem. If you let the fast-changing gradients from a new input update your slow, long-term knowledge at the same time,
Catastrophic forgetting.
you get catastrophic forgetting. The new stuff just overwrites the old.
So the exclusive flow makes sure that while the inner memory is learning the immediate context, it doesn't destabilize the slower, abstract knowledge. It's like giving the LLM an artificial sleep cycle.
That's a perfect analogy. And it leads us straight to their architectural solution, the Continuum Memory System, or CMS.
CMS is where this all becomes a concrete architecture, not just a theory.
Exactly. It organizes the model's knowledge into a chain of MLP blocks. But the key is, each block is tied to a specific and progressively slower update frequency.
So you could have one MLP block that updates every other step, learning short-term patterns, and another block at the end of the chain that only updates every, say, 1,000 steps.
And that super slow block is forced to learn only the most abstract foundational knowledge that holds true over that entire long period. It solves the system's consolidation problem.
And they point out that a standard transformer is just a CMS where the number of levels, K, is 1.
Right. It only has one update frequency, which is why it can't do this.
And when they combine all these ideas, the multi-timescale architecture and self-modifying principles, they get HOPE, a self-referential learning module.
HOPE is the real-world test of these nested learning principles.
Yeah.
And the results they got are, well, they're very compelling.
They tested it at moderate scale, 760 million and 1.3 billion parameters. What did they find?
On language modeling, it got significantly lower perplexity. On common sense reasoning, higher accuracy. It outperformed traditional transformers, but also newer recurrent networks like RetNet and DeltaNet.
And they pin that success directly on the architecture's ability to dynamically change its own components based on the context, all stabilized by that deep multi-speed memory system, the CMS.
So if we just, pull back for a second and look at the big picture, nested learning really changes the goal of architectural research.
We stop focusing on just architectural depth.
Right, just stacking more layers.
Wow.
And we start focusing on temporal depth.
Temporal depth, I like that. Nested optimization, these deliberate multi-timescale updates. It feels like a much more, biologically plausible way of building things.
It is. It gives us a clear mathematical and neuroscientific foundation for building systems that can actually learn continually. Yeah. This is how we get LLMs beyond being just static databases.
The framework seems to show that everything we've been building, from optimizers to attention, is at its core just associative memory.
We've always been building memory systems. We just weren't designing them as these proper hierarchies of memory.
And that brings us to the final, really provocative thought they leave us with. The sources say that architectures like the transformer are basically just linear layers with different frequency updates. We've been using maybe 2, or at most 3, implicit memory levels without even realizing it.
So the question is, what happens next? What new emergent capabilities will we unlock when we intentionally design models with 5 or 10 or 20 distinct higher-order memory levels?
Each one optimized for a different timescale, all working together to achieve genuine systems consolidation.
We might finally get what we've been after all along, a machine learning system that truly never stops learning.
That is definitely something to mull over. Thank you for diving deep with us.
And that brings us to the end of another deep dive into the world of generative AI.
Thank you for tuning in to GenAI Level Up. If you found this episode valuable, please consider subscribing and leaving a review on your favorite podcast platform. It helps us reach more curious minds like yours.
Join us next time as we continue to explore the cutting edge of artificial intelligence. Until then, keep learning, stay curious, and continue to level up.